So now we're going to be starting section 5.3 of your textbook, which is on sample spaces and tree diagrams. I'm going to split this into two videos. In this one, we're just going to talk about sample spaces, and then the next video, which will be up as part of next week's class on Tuesday, will be on tree diagrams. So first we'll talk about what a sample space is. A sample space is a set of all equally likely possible outcomes of an experiment. And it's important that everything inside the sample space has the same probability. Okay, so now let's look at this example where we're going to find the sample space for flipping 1 coin, for flipping 2 coins, and for flipping 3 coins. So the sample space for flipping 1 coin, right, we just want to include all equally likely possible outcomes that can happen when we flip 1 coin, right? And we know the only things that could possibly happen is we could either land on heads or we could land on tails. That's it. So that's our sample space for flipping 1 coin. Now if we're flipping 2 coins, there's going to be more things that could happen when we do this, right? So first that could happen, well, both coins could land on heads. That's one possibility. We could have 1 coin land on heads and another coin land on tails. But we could also have, well, the first coin could land on tails and the second coin could land on heads. Or we could have both coins land on tails. Now we'll take a look at what would happen if we want to do if we wanted to find the sample space for flipping 3 coins. Okay, so now the first thing that could happen is, let's say all of them land on heads. And sometimes when you're finding sample spaces for bigger situations, it's helpful to try and list out your different possible outcomes in more of a systematic way. So first we'll go through 3 heads. Now let's see what happens if we land on 2 heads and 1 tail. Right, so we could have the first 2 coins land on heads and the third one lands on tails. We could have, right, head, tails, heads. We could have tails, heads, heads. Right, and I think that's all of the ways we could get 2 heads and 1 tail. Well, now let's see what happens if we end up with 2 tails and 1 head. Right, so we can just flip the positions of the T's and H's. And that shows us all of the ways that can happen. And now the last possible outcome would just be getting all 3 tails. So this whole thing here would be our sample space for flipping 3 coins. Okay, so let's look at this problem now. Okay, so let's say here we have 6 pieces of candy. We know that 2 of them are Smarties. We don't know about the other 4. We want to randomly take out 2 of the pieces and find the probability that both of the pieces we take out are Smarties. Okay, so one way that we could do this problem is by drawing a sample space. And one of the good things about sample spaces is that they can help you solve certain probability problems. They aren't always useful depending on what type of problem it is, but in this one, a sample space isn't a bad, route to take. So first what we're going to do is, this isn't just like heads or tails. We should call the pieces of candy something. So we're going to give them names or numbers in this case. Right, so we'll call the pieces of candy 1, 2, 3, and 4 for the first ones. And then what we'll do is we will call the 2 Smartie pieces, let's get another color for this, we can call them S1 and S2 for the first Smartie and for the second Smartie. Okay. Now we can start listing our sample space. There's a couple of different ways that we could construct this sample space. So first we'll do it where we're taking them out in groups. So we'll think about what pieces of candy we could take out. So we could take out any 2 of these at the same time. So first let's say we're taking out the first piece and the second piece, right? That's one grouping that we could take out. Then let's say we take out the first piece and the third piece, the first piece and the fourth piece, the first piece and the first Smartie, or we could take out the first piece and the second Smartie. So this is every possible way we could take out the first piece and then one of the other pieces. Now let's go through what else we could do. Well, we could take out the second piece, and we could take out the third piece along with it. We could take out the second and the fourth piece. Now keep in mind, we've already seen what happens here if we take out the second and the first. We could take out the second and, actually, yeah, no. We could take out the second and the first Smartie, or the second and the second Smartie. Okay, so now let's go back here. We could now take out the third piece. And well, we've taken the third piece out with the second one, and we've taken the third piece out with the first one. So we could take the third piece out with the fourth. We could take the third piece out with the first Smartie. Or we could take the third piece out with the second Smartie. What else could we do? We could take the fourth piece out first now, and we could, we've already seen what happens. Well, we could take the fourth piece out with the third, we could take the fourth piece out with the second, we could take the fourth piece out with the first. We could also take the fourth piece out with the first Smartie, and we could take the fourth piece out with the second Smartie. And now we could also take out two Smarties together. We could take out the first Smartie and the second Smartie. Right? Because we've already seen what happens if we take the first Smartie out with the fourth, third, second, or first piece. Right? Same for the second. We've seen what happens if we take the second Smartie out with the fourth, the third, the second, or the first. So now we can count up how many possibilities there are in here. So this is 15 possible outcomes in this sample space. Right? If we count up everything here. And there's one possible way to take both of them out over here. So 1 out of 15 would be our probability for this. Okay, so now we'll look at one more probability problem we can solve by listing out the sample space. Okay, so in this example, we're going to suppose that a fair die is rolled twice. And now we want to find the probability that both of the rolls are even, the sum of the rolls is less than 10, at least one roll is odd, and that the first roll is 2 more than the second roll. So in this problem, we're being told that we're rolling one die 2 times. If you were told that you're rolling 2 dice, the sample space we generate is going to end up being the same. So, right, instead of just sitting here and trying to think of everything that could possibly happen, we're going to kind of systematically list out everything that could possibly happen. So we'll consider what would happen on the first roll first. So the first thing that could happen is, both of the faces could land on 1, right? We could get 1 for the first roll and 1 for the second roll, right? So this will be first roll, and this one will be for the second roll. Then we could get 1 for the first roll and 2 for the second, 1 and then 3, 1 and 4, 1 and 5, or 1 and 6. And this is everything that can happen if we land on the number 1 for the first roll, and then we would cycle through everything else. Now, let's say we don't land on 1 for the first roll. Well, we could land on 2 for the first roll, right? And then land on 1 for the second, right? Or we could land on 2 for the first and 2 for the second, 2 for the first, 3 for the second, and so on. Right? And we would just go on like this for all of the other numbers on the die. So here we have generated the entire sample space. So everything in here, these are the 36 possible outcomes for if we roll 2 dice or if we roll 1 die 2 times. Right, so now let's go back to what these questions were. So first we want to find the probability that both rolls are even. So now that we have our sample space listed out like this, I'm just going to go in here and look for all instances where both rolls are even. So here they're both even, 2, 2, 2, 4, 2, 6, 4, 6, 4, 4, 4, 2, 6, 2, 6, 4, 6, 6. Okay. So both rolls being even, we have, let's see, this is 1, 2, 3, 4, 5, 6, 7, 8, 9 out of 36 possibilities. Okay. Now the next one is the sum of the rolls is less than 10. Okay, so now this one's a little bit tricky, and there is a small trick that I can show you if your sample space is listed this way. And we want to look at what the sums of all of the rolls are. Well, if we look over here, right, 1 plus 1 is going to give us 2. Right, now if we look at this one, we have 1 plus 2 and 2 plus 1 are both going to give us the same sum of 3. Okay, so this is going to give us 3. Now if we look here, 1 plus 3, 2 plus 2, 3 plus 1, all give us 4. And this pattern actually continues throughout the rest of the sample space. Right, so you're like, 5 plus 1, 4 plus 2, 3 plus 3, these all add up to 6. Everything along the middle diagonal adds up to 7. And then the next one, everything here adds up to 8. These guys all add up to 9. These guys all add up to 10. These guys add to 11. And 6 plus 6 adds up to 12. Okay. So here we have all of the sums of the rolls. And what were they asking us? The sum of the two rolls together is less than 10. So here, if we want to, let's say we want to try and count up everything where the sums are less than 10. Okay, well, that's less than 10. This is less than 10. These guys are less than 10. Everything up here. It's actually quicker if we were to count everything that isn't less than 10. So these guys add up to 10, so that's not less than 10. And then, 11 and 12 also aren't less than 10. So if we kind of, circle off this area, these guys are all greater than 10. So we can make use of the complement here to have a faster time counting. So the sum of the rolls being less than 10, well, if we do 36 out of 36, which is everything, minus everything that's greater than 10, so that's 1, 2, 3, 4, 5, 6, 6 out of 36, gives us 30 out of 36. Right, now what we also could have done is we could have counted everything else over here. We could have counted everything else in this sample space that is everything that's less than 10 when we look at the sum, but that would take forever to do. So this is an example where if you're familiar with how complements work, you have a little bit less of a hassle finding the answer. Okay. Now let's see here. They're asking us find the probability that at least one roll is odd. So at least one roll is odd, right, means at least one means we definitely need one that's odd, but it also means 2 odd rolls is okay. So another way that we could rephrase this is by saying that we have, right, 1 or 2 odd numbers, or 1 or 2 odd rolls. Okay, so, all right, so let's see. Okay, so we're looking to see that we have at least one roll is odd. So that means either we have one roll that's odd or both of the rolls are odd, meaning 2 of them are odd. So if we look over here, well, if 1 is our first roll, well, obviously that meets the requirement of, 1 or 2 of them. Now if we go, and the same would be true for everywhere else where we're rolling in, an odd number first. All right, so all of these columns are automatically going to be counted for that. Now if we go over here, well, these guys are even. So the only things that we're not counting is, well, over here when we roll 2 evens. Right, so everywhere here we have 1 even and 1 odd. Okay, and what's interesting now is we might notice that if we look at what we did for part A, where both rolls are even, those are the only numbers that, you know, in our sample space that haven't been circled or haven't been included here. So what we did in C ended up being the complement in A, right? Sometimes you don't notice this until you go through and solve the problem, but as you do more problems, you may begin to recognize things like this and have a, you know, quicker time solving the problem. So now that we recognize that's the complement, instead of counting up all of these numbers that are circled in yellow, which, you know, again, would take forever, we have our probability already calculated over here, 9 out of 36, and we can just subtract that from 36 out of 36. Okay, so and we end up with 27 out of 36. Okay, so now let's go to D. D is saying we want to find the probability that the first roll is 2 more than the second roll. Okay, so we could look for these in here, but in this case it may be easier to list out what our possibilities are and then look for them. So if we want our first roll to be, let's see, 2 more than the second roll, right? Well, if our second roll, we'll list out, okay, so we'll list out some possibilities. Okay, so let's see, our second roll could be, right, let's see, if our second roll is 1 and our first roll is 2 more than that, well, 2 more than that would be 3, right? So this is one possibility that we have. Now, if our second roll is 2 and our first roll is 2 more than that, then we'd have 4. Then let's see, we could end up with 3 and 5, and we could end up with 4 and 6, and then that's it. There's no other rolls that will, where the first one is going to be 2 more than the second. Okay. So now if we go back here and see how many possibilities there are, what do we have here? Okay, so 3 and 1, we have 4 and 2. Oh, sorry, okay, so we had 3 and 1, 4 and 2. We had 5 and 3, and 6 and 4. So this was 4 distinct possibilities. So this probability ended up being 4 out of 36.